Okay, so this is what we wrote at the beginning of stream 1, at first day. And remember how we went through using the definition of a derivative is actually just limits, right? We're used to that. Limit of h equals 0 of f of x plus h minus f of x all over h. We went through increasing the power of a polynomial with a constant, identity, square, cube. The constant was a 0 power, and the derivative was 0. And the f of x, the function is x, so the first power of the derivative was 1. When it was x squared, the derivative was 2x. And when we had x cubed, notice it got more and more complicated as that went up. X cubed became 3x squared. And what we decided was the shortcut for called the power root. Which actually each time was a polynomial. It was a monomial, but what was happening with the power? 3 or x cubed, where did the 3 go? And 5, and then what did the power do? Decrease by 1. So this is what we wrote down. For this is the power rule. Given any of this is for all polynomials. Given any power, bring the power down within the power of 0 and decrease the exponent by 1. Okay, so instead of working at long ways, we did limit from going to get super complicated with x to the 4th. The derivative, and this is the notation, one of the notations we use for derivative, we'll see in the next page who created that notation. What would the derivative be? Bring the power in front. What's the power? Bring the power in front. X to the third. See, so much easier than going through this limit notation. Let's do it. Okay, so flip it over. We have a bunch of different notations. There are many ways to denote the, I think that's a typo, to denote the derivative of a function. Talking this was discovered about around the same time as two different mathematicians, Sir Isaac Newton and what do you think this guy's name? Leibniz. There's not on it. Leibniz. Like you lie, Leibniz. If you watch that video about the invention of calculus, here are the most common types of notations. In this middle column, this is how we say it. The far left column is how it's written. So this is what I wrote on the first page, F with this little tick mark. This is read F prime of X. It's very common. Allows us to evaluate a specific X value. It's not F times X, it's F of X. It's function notation, but the little tick mark means it's the first derivative. The 2 tick marks would be the second derivative. 3 tick marks, third derivative. It was this is Newton's notation. Okay? Or we could write y prime. That would be a y. Maybe our function is written as y equals. If you take the derivative of y, it's y prime. Okay, so y with the tick mark. The tick mark means prime. This is nice and brief, but it doesn't name the independent variable. Okay, it doesn't give us the x in order to evaluate for any value of x. So that is a disadvantage to this notation. Okay, this one, dy over dx is read dy dx. Okay, dy dx, or you could say the derivative of y is in the numerator with respect to x. So with respect to, that's whatever variable is in the denominator. These are all notations for the same thing though. They all mean derivative. dy dx, we can also say the derivative of y, the equation y equals this function, with respect to the x variable. Okay? This was Leibniz's notation, and he used both the variable and uses the derivative. Okay, we actually use this one a lot. We've used both Leibniz and use the first one and the third one a lot. So they're both useful depending on what type of problem we're doing. Okay, then we can also have another version of Leibniz's notation is dx dx. And you if my function is not y equals, it's f of x equals the derivative of f with respect to x. Notice the denominator is always the variable we're having respect to, with respect to x. Okay, it emphasizes the function's name. This one I don't think is as common. I don't really use this as much. I won't use dy dx. And the last one here, this is also not as common, but ddx of f of x. ddx of f of x. ddx means you're taking the derivative of. ddx means the derivative of. That's the ddx. One second. You're taking the derivative and you're saying you see ddx. F of x is just a function that you're taking the derivative of. So f at x, that's just your function. Okay, it emphasizes the idea that differentiation is an operation performed on a function. So if you say just ddx, it doesn't say dy dx, it doesn't say df dx. ddx just means that you're taking the derivative of whatever's following it. No, this is not division. No. No, that was actually a really good question. These don't just cancel out. So let's look at some examples here. Notice what's the function called? Is it f of x? It's y. So we have a few options. We could do y prime, or we could do dy dx. Both mean the derivative. We're going to find the derivative of all these examples. Let's on this first one do y prime. So we're going to take the derivative. Oh, actually, instead of find y prime. The derivative of y, and then do d dx of that, which means I'm going to get y prime. If I have a d dx, that means I take the derivative. But if you take the derivative on one side, so if you do the other side, just normal equation work, and do it one side, do the other. So we have d dx, the right-hand side, which means the sides are parallel. Maybe a different color, it's kind of hard to see. This 5 multiplies in front. So I have 5 times 4x. And then what happens to the exponent? Decreases by 1, so it becomes a 4. Minus a 2 multiplies in front. Minus 2 times 3 to the x, what power? 1, we took the derivative, the power decreases. Plus 5x, what's the power on that x? 1. So you can practice doing the same thing, but does anything I want to do anything? No, we have to decrease the exponent. If it was 1, what is the exponent now? 0. How many x's are with the minus 7? This is x to the 0 power, right? So we times by 0 in front, times by 0 in front, it's just 0. So when you take the derivative of a constant, it just becomes 0. That was the very first derivative we did on the front side. It was derivative of a constant will always equal 0. So I'll just go to now and simplify. I didn't make much space. Y prime equals 20. Multiply those. X to the 4th minus, multiply those. 6x. Ooh, what's x to the 0 power? 1. So this is 5 times 1 times 1, which is just a positive 5. So there is y prime. You need the prime. If you just put y, just say this is the original function. You can just create a second function, which is the derivative. And remember that the limit of h approaches 0 of f of x plus h minus f of x over h. We apply that to a function at a certain x value. What can it give us? Slope. So the derivative is finding the slope at any x value. If I want to know the slope of the original function at, say, 2, I just plug in a 2. Into my derivative, and I know the slope there. Or I want to know the slope of my original function at 10. In the derivative, I'm putting 10. I have my slope. Okay? It's way faster than doing that limit notation every time, right? Because as you saw on the power increases, it gets really crazy really fast. Okay, let's practice some of these other notations. Instead of y equals, let's put it as f of x equals, practice the other notations. Okay, how do we write the derivative of an f of x function. We're going to try, okay, there's some options. Yeah, I probably know F prime of X. That's more common. The two at the very bottom, these two at the very bottom, aren't as common. But I would write as F prime of X. F prime of X equals, take the 6 and multiply it to the 7. What is 6 times 7? 42. X to the what power? 5. Plus, take the 4, multiply it in front. What do we get? 8. So the power always multiplies in front, and then they decrease instead of x to the 4th. It's now x to the 3rd. Negative 5. Bring over the 3. What do we have? 15. Negative 15. X to the 2nd power. How many x's are on pi? 0, because pi is a, and then we're going to consider constant. We take the derivative of a constant, it's just 0. So there is our derivative. Okay? Now, number 3, let's try a different notation. I want you to actually do this notation right here. The third notation, dy dx. When we take the derivative of y, another way to write it is dy dx. Okay? I want you to try it now. You know the power thing, just multiply in front. Decrease the exponent by 1. So we're really not challenging because there's a fraction. I think you can do it. Good. Okay, and number 4, I'll let you choose your notation for the y. We take the derivative of y. Choose your notation. No, you're right. That's right. Now just multiply those together. Then do number 4, you finish choosing your notation, whichever is your favorite. Then that's it. That's it. Okay. Good. This is an equation, so you have to carry it on an equal sign, and you have to say y prime or dy dx. This one's what we're doing. It's not dx dx, it's dy dx. This is when you multiply your 6, you times into the numerator, and times into the denominator. Good. Good job, guys. This one. This term is right. These two. Okay. When you put it up, it's actually negative 2, right? And if you decrease it, you increase. Yep. Here we go on every time. Well, if you do the power rule again, that's in the second derivative. We'll do that.
But that is
We're going to take the power rule probably one more time in the power. If it's an x cubed, I think you're going to make 4 times. You can clearly take the derivative until you end up with a constant, and after you take the derivative of constant, you do that. Okay. Oh, that last one is tricky. Tricky. Oh. No. Wait, maybe. What's that? 2 and 3, right? It should be in this window. Okay, looks like we should do number 4. I think that was number 3. You all good? So you can either say y prime or f of x, f prime of x. Okay, actually first I'm going to rewrite it. Unequals and fractions. Unequals and fractions, when we do get derivative tests, we didn't have to do. And once we know a lot of derivatives, you're going to have to pass a 100% derivative test. You can retake this until you get 100%. We'll do the same thing with intervals. And the funny thing is, those can be the hard ones, but they can't help the easy ones. And if it's a polynomial, those are the easy ones. This x squared, what happens if I bring it up? It'll be negative 2. So 3x to the negative 2. If I bring that x up, plus x to the negative 1. Minus 1/2 x to the 4. Okay, multiply. Negative 2 times 3. Negative 6. Now here's the hard part. We're going to decrease. It's not negative 1. It'll become negative 3. Plus, oops, actually not plus, huh? If you bring the, this is y prime or f prime. Bring the negative in front. Negative x, and we have to decrease. Negative 1, subtract 1. Negative 2. Bring it forward, and we'll put in front. We have negative 1/2 times 4 is negative 2. X to the third power. Then I would picture negative exponents, because there's some things we never leave, right? Negative exponents is one of them. Y prime equals negative 6. Those are new. Negative 6 has the first power exponent. That's positive. Only the x moves down to x cubed. There was a denominator. So it makes sense you only move the x part down. Minus, what's this one? 1 over x squared. This one's good to go. It's already positive. So minus 2x cubed. That is our derivative. Okay? I think a lot of you were close. Just your power was wrong because you have negative 1 minus 1, or negative 2 minus 1 equals negative 1. So make sure they run in their direction they're stretching. Any questions on those? Okay. In your book, the first definition is this one. We take the derivative, we apply the definition with that, right? In your book, there's an alternate definition. Would you open up your books, please, to section 201? It's very similar, but it's good to be aware of. Okay, 3.1 in your book for the alternate definition. It is on page. The original definition is page 99. The alternate definition is page 100. I want you to look back and forth at 99 and 100. They're both of those 10 boxes. Discuss period for what's similar and what is different between the regular definition of a derivative and the alternate definition of a derivative. Page 99 and 100 are both definitions of derivative. Did you hear what Chris said? Look at tangent. The first one. The other one looks like an old school formula because it's creating a secant line. But notice what is so limited though, that's a similarity. Let's write this on my paper here. F prime of A equals the limit of x approaches A of f of x minus f of A over x minus A. And what if x is approaching A? What if x was A? What would the denominator be? 0. Because then the gap between our 2 points would no longer be a secant line, it would be a tangent line. So it's very similar because we're shortening, that's not a word. We're making the gap shorter. Shortening, I don't think that's a word. I said short, didn't mean that. Yeah. We're making the gap smaller. As x is approaching a, this gap is getting smaller. Okay, so yes, it's just like a secant. So, differentiate shape f of x equals x to the square root of x using an alternate definition. Okay, so f prime of a, because it says f of x. F prime of a, so a is kind of like an h, and the other definition is an h, right? This definition is an a. And the limit as x is approaching this value of a, f of x. What is f of x? Square root of x. It's just the original f of x. I told you right there. F of x is the square root of x. Minus. What? What's f of a? A square root of a? Just square root of a. We take the a and plug it in. So we get square root of a over x minus a. Now in the other form, the everything without h cancels out, right? And without the h, and the denominator division by 0 goes away. If we put a right now, like division by 0, it's a problem. So we're going to manipulate it by using a conjugate. Conjugate. Okay? What would a conjugate be? So you always have to use a conjugate of the denominator. Oh, we can use a conjugate of the numerator. What's the conjugate of the numerator? Let's try that. So we're going to multiply by a fancy form of 1, square root of x plus square root of a, over, it's the same thing, so that's just a fancy form of 1. Okay, let's multiply them together. What is root x times root x? Just x, yeah. What is root x times root a? So it's a positive root ax, because inside the radicals just multiply together, the x and the a multiply together. What is negative root a times root x? Ax. The radicals just multiply together. The radicals are what's under the square root. And negative a root a, excuse me, times root a. Negative a, because the square root times the square root, especially if they have the same radical, just cancels out, right? So the pair. All over, don't forget, we have a limit. Some of you on your test as well, you'll get that you're wrong. Once you plug it in, you don't have the limit anymore. The limit must be written until you plug in. So you haven't plugged in yet, so we can write that. And we put in the denominator. X squared of x. Plus x squared of a. You agree with that? Okay, and the numerator, I think, is where the action's going to happen. Those just cancel out a root x minus a root x. That's what should happen with the conjugate. That's the point of the conjugate. You have to have opposite signs in order for those to cancel out. So I'm going to, as x approaches a, of x minus a, over x root x plus x root a. Nothing in the denominator cancels out. I'm keeping the denominator like terms. Even close to being like terms. Don't cancel out like terms there. How about radicals like terms? Same radicals, exactly right. Same radican. So, this one, root x. This one, root x. They have something in common. Can we factor out what they have in common? have this x, they have root x in common, right? So in my denominator, root x in common, let's factor it out. When I factor out, this is like factoring by grouping. We have 4 terms in factoring. Then we're factoring by grouping. Take the down in common, factor it out. It makes us with an x and a minus a. X minus a. The other like terms. Root a and root a. So something in common. We pull out a positive root a. What remains? I take off the root a and we back it out and do dividing. Get x minus a. Who has questions on this? Take what they have in common. The remainder is the coefficient. And guess what? Matchy. The match? Everything else in common. And the numerator is just this. Don't forget about the limit. Now you run out of space to wait for the grader on your response to figure out where you went with your thoughts. It's draw an arrow. We still need the limit because we haven't plugged in yet. They have something else in common. That's not that thing that they was. If I pull out what they have in common, is x minus a. Something remains. If I take off x minus a, what remains? Square root x. Take off x minus a, what remains? Positive root a. So square root x. Positive root a. What was the point of doing all that? So it's not variance of 0. So can you see what's happening? What's going to happen? What will be? It will cross out. Which part crosses out? The x minus a. That's the whole point of factoring. Like the other definition, we factor out an h, so we can cancel out. Here we have to do some extra manipulation with a conjugate. So first we have a conjugate, and then we're going to factor by grouping. And it remains the limit of x approaches a of 1 over root a plus root a. Do we have it? Oops, excuse me, root x. Do we have a problem with division by 0 now? No. So can you find the limit? Once you plug in, you drop the limit as x approaches a. Which one gets plugged into, the x or the a? The x is going to a. So we get 1 over root a plus root a. Chris, what is that? Christopher? No. Christian. What? Sorry, bring that. Christian, what is this thing on the way out of? Over. Really close. Yeah, I think I just found what it was. 2 roots of a, because I like terms. Good. Okay. So, if you were asked, it's kind of a weird situation, you need to get rid of both definitions of a derivative, the alternative, and the original. Okay, put it all to the back. How does the derivative relate to the original function graphically? How does the derivative relate to the original function graphically? So, here's our original function. It's going to be cubic because when we get to the derivative multiplied 3. So there are 3 factors. This is actually really nice right here. We can see a lot of things about the graph based on these 3 factors. Let's do this graph. This cubic graph. How can we graph it? What do these factors tell us on the graph? Make it bigger. What does x plus 2x minus 2 tell us on the graph? On this cubic function. Number 1. So it tells us 3 things on the graph. denominator, we have potentially asymptotes or moles, but these are not in the denominator. Ready? The x-intercepts. Remember, solution, zeros, roots, x-intercepts. Yeah, that's pretty. So think of the zero property. So each equals 0, x equals 0. So that one equals 0, x plus 2 equals 0, and x minus 2 equals 0. We have the factors. And it tells us all of our x-intercepts. So the x-intercepts happen at 0. What's this one? -2 and +2. 0, -2, and +2. Over here, there we go. So it's got those on the x-axis. We have an intersection of 0, -2, and +2. Okay? What else do we know about this graph? What does the graph look like? Kind of like an S shape, like that. Okay, so go this way. Okay, so we have this shape. Can we find the point at -1 and the point at 1? Okay, the point at n, can you find the y value if we plug in -1 and the y value if we plug in +1? So you do that by function notation f of -1. -1 and -1 plus 2 and -1 minus 2. And f of 1. Do you know between these points when we get the minimum or maximum and Li, we kind of have a general shape if we know this is positive. X times X times X is going to be a positive cubic. Okay, what do you get when you plug in -1? 3. What do you get when you plug in +1? -3. Good, good. So I'm going to get you a pencil because I'm going to be plotting multiple graphs on the same coordinate plane. Okay, let's take a couple colored pencils, pass it down. Pick a color and grab the cubic function that goes through. These are what we call critical points. Okay, when you're done with graphing that, pick a different color, and we're going to find the derivative f of x. Now, f of x first, 0x plus 2 times x minus 2 is when you want to find the other. X squared minus 4. Good. So we have x times x squared minus 4. Oh, I just got really busy. F of x equals x cubed minus 4x. Okay, so what is, this is a polynomial. Oh man. We're on spinner right now. Okay. It comes out. Catch me. What's that prime? Good. You're trying to your head. X squared minus 4. What's the function of that? That's a quadratic. So as we take the derivative, the function is decreased in power. Cubic becomes a quadratic. If we took the next derivative, what would it become? Linear. And the next derivative, you want to become. Okay, so we're going to graph this. We need some critical points. What are some points to look for in a quadratic when we're graphing? The one. Don't care necessarily about the y or something at all. There's a very important point on a quadratic. So the V. The vertex. You know the formula to find vertex? What is the x-coordinate of the vertex? A long time ago. It's like grade 2 math. Good, good. Negative 0 on the 2a's. Beginning and the end of the quadratic formula. This is a quadratic. It's finding the axis of symmetry. Axis of symmetry is negative b all over 2a. Right. What do you do pop this result? X is equal to negative b all over 2a. Okay? So when you find x, the x coordinate of the vertex, you put it in, you have the y coordinate of the vertex. So solve for the axis of symmetry. What's the x coordinate of the vertex? It's b. Is b negative 4? No, b is 0. The b to the first power, the x to the first power is missing. So b is actually 0 all over 2 times 3. So our x coordinate is 0. Now I can find the y coordinate. Right? F prime of 0, we have the prime because we've done the derivative. F prime of 0 is 3 times 0 squared minus 4, so we get negative 4. So our vertex is the point 0, negative 4. We take your second colored pencil and plot the vertex 0, comma, negative 4. Okay? What type of graph is F prime? What would it become? What type of function would we call it? Quadratic. So we have the vertex. Do we know this quadratic is going to be concave up or concave down? 3x squared, that would be which? Up. So we know it's going to have to cross the x-axis. So how do we find those points where it crosses the x-axis? And 0 for y. If you're on the x-axis, your height is 0. So we need to plug in 0 for y and solve. So 0 equals 3x squared minus 4 and find the x-intercepts. Actually, I lied about two of the graphs on the same. So we're going to actually graph this one and the second graph. But we want to look at the relation between the first graph and the second graph, so it doesn't get too crazy. What is our x-intercepts? What are our x-intercepts? So we have 4/3 equals x squared. We square root it. X equals 2 over 3, that would be missing one thing, that's every vote. Plus or minus 2 over root 3. So you apply the square root yourself, you don't know if it's the principal root or the negative root, so it's plus or minus. Okay, so with that second color, here at negative 4, we're actually going to go to the back row. Negative 4, what is 2 over root 3? That's something that you really get in your head, but 2 divided by root 3 is about 1.15. Okay, so just past 1, and also negative 1.15. So about right here, and about right here. Okay, now we're going to do it again. F double prime. See how there's 2 tick marks? F double prime was in the power rule. Well, F prime was 3x squared minus 4. You should get to the point where you can just do this in your head. And some of you are already getting there. Christine, what's the second derivative? Zero. Good. So it's now what type of a function? Linear. I expected. We already talked about that. Linear. So each time the power is decreasing, the type of function is changing. And 6x, what does it cross the x-axis? At 0. It has a slope of 6. So get a third color. I need to make this smaller because I can't see everything. Get a third color. Red. I use red. Crossing at 0. We go up 6 over 1, which is equivalent to the other graph. Down 6 over 1. And it's now linear. Okay, what about F triple prime? F triple prime. If F double prime of x was 6x, that's F triple prime. So 6, what type of a function is just 6? F triple prime of x equals 6. What type of function is that? Constant. What type of a line does that look like? Don't say straight, because all lines are straight. You can say that, but I said it's that. It's horizontal through 6. This one. I have not changed. Okay, now what we're going to do is look at relationships that happen as we take the derivative. So I can see all of them. I'm going to do the slightly larger one. Almost. Okay, so we went from a cubic, take the first derivative, we go quadratic, take it, the second derivative, we go linear, take the derivative again, we go constant. Ooh, I don't like this image of this. We do between the 150 and 200. Okay. Okay, we just won't see the bottom one for right now. We might be looking at what happens from plate to plate. I want you to look at, I'm going to highlight here. Until we reach a critical point at the maximum, that happened at -1, right? X equals -1. What is the derivative doing until -1? The position function is increasing. Yes, what's the derivative function doing? Decreasing, true. We don't see much of a derivative function besides decreasing. That's one. Okay, in touch with the x-axis at -1, but before -1, where is it compared to the x-axis? It's above, so what type of numbers are those? Positive numbers. Okay, let's look at the intersection. From -1, so very thick, -1 to this minimum here, from -1 to x equals +1. That's here on derivative. On the position function, this is the original, we'll name this x called the position function. From -1 to +1, the original function is doing what? Decreasing. And its derivative in that same interval of time is what? Okay, but can you give me one thing that does, which is two things? Yes, it decreases and increases, but can you give me one thing? What is it? Hello? What kind of numbers are those? Negative. So when we're increasing, the derivative is, no, positive. And we're increasing the derivative is positive. When the position function is decreasing, the derivative is negative. Make sure this pattern continues. which is a minimum, that starts increasing again at -1. So the derivative should be positive. Also, let's look at something else. These critical points. The maximum is not a maximum of a derivative. What is it? An x-intercept. What about the minimum of the position function? What is it on the derivative? X-intercept. So, when you're changing from increasing to decreasing, that's a critical point. Increasing to decreasing. You're going up and then down. So you're positive and then you're negative. Positive, negative, right? I still did my little finger. I went up and I went down. So positive slope, negative slope. Slope. The relative derivative is slope, positive slope, negative slope. Positive numbers, negative numbers. And then here I change. They're going down and then up. Negative slope, positive slope. So negative slope is a negative, positive slope is a positive. And -1 and 1 are maximum minimum points. Maximum mins become our x-intercept. The picture continues. Okay, looking down below, comparing our quadratic to the linear. So we were decreasing, oops, I mean in color because it keeps decreasing, right? Why don't I use pink? The quadratic decreases until the vertex, correct? So decreasing until x is 0, which means until x is 0, the decrease in the slope or the linear line should be what type of numbers? Hey, is that true? Yes. And then, about orange. It starts increasing, that is kind of orange, increasing from 0 and beyond. So this graph should be positive, and that minimum point, the critical point, became a x-intercept. And we continued. This is interesting. From this graph to this graph, the graph is continuously increasing. Is it ever going to decrease? No. So where is the line? Possible is and you know it's constant? What's the slope of this line? Is it a constant slope? Constant slope, that's right, it's constant. Spotlight, let's slope of 0. So some interesting relationships that happen. Let's go fill in this box, see if we've captured everything that just went on. How is the derivative of prime related to the position function? The maximum is of f, the original function. Why not put the what of the derivative? The maximum is become what in the derivative? The x-intercepts. The maximum is of the previous function, whatever function you were doing, becomes the x-intercepts. And then the other thing. What happens on f prime when the slope of the tangent line is 0? What happens on f prime when the slope of the tangent line is 0? So let's look at the original position function. When do I get a slope of a tangent line equaling to 0? I follow my graph up. When does the slope of the tangent line equal 0? The maximum and the minimum. So here, that's not a 0, so we can actually draw a 0. So maximum and minimum. In the derivative, what's happening right there? Again, the x-intercepts. But this graph actually phrased differently. What happens on f prime when the slope of the tangent line of f? That's exactly what it is answer, right? I can put f prime. So the slope of the tangent line is 0 on f. The derivative has those x-intercepts again. You get an x-intercept when f prime has a tangent line equal to 0. You bit and x intercept when, now say on, this is when, on f prime, when f of TL, tangent line, so the f's tangent line is 0. And remember, tangent line is actually showing you what on the graph? Slopes. So we're taking the derivative, we're actually finding the slope of the original function. Okay, so keep that in mind. When f is increasing, f prime is doing what? So increasing, this yellow section, when f was increasing until x equals -1, f prime was not necessarily positive. That's what it means. Positive. So it looks like it's decreasing, but it decreases past that point, right? It would just stop decreasing there. It decreases until, well, past the point. So what we're looking at is the slope. We're increasing, our slope is positive. Okay? So f is increasing, f prime is positive or above the x-axis. So positive. Versus when f is decreasing, f prime is where compared to the x-axis? Below, so that means those numbers are negative. That was it. Any questions? Yes. How do you find the slopes of curves? You can find slopes of lines, right? Because it's constant. The curve is always changing. The slope is always changing. So the derivative helps us find the slope at any point on any curve. Okay? I have a new homework log for you guys. I have, what is this? Oh, just a short one. There's a nice. Okay. There's everyone got some that. Yeah. Oh, I forgot to have you guys pick new seats. So next time, new seats. So I test you guys picking new seats, but you get it as you change up once in a while and you work with it. Okay, take one, toss them around. You all get one? Okay. No. Because we didn't know how to take those of all types of functions. Before and then, Halloween. Then, like, before Halloween. Eventually before Halloween. Alright, so we have 20 minutes here. I'm not open up to buddy up with my neighbor. Yeah, thanks. Yeah. We have questions on 3.1. Nothing's due next time. We had a test last time. So just questions on 3.1 next time. One. Open up your book. Okay, on each problem, please don't just write down the derivative. Please write the problem down first using correct notation. If it says f of x, do the derivative with respect to that notation. why the X is more useful. Some of the different types of notations. I think the most useful ones, what's the highlighter? There we go. I think the most useful ones would be this one, and this one. One of which belongs to Newton, or was covered by Newton, the other one was Leibniz.